This video is a demonstration of a Combline Diplexer design using EQR Opt Microwave Office. EQR Opt Microwave Office is a custom optimization engine that assumes you're looking for a Chebyshev transfer function, or you're trying to optimize a Chebyshev filter. It can be applied to single filters, diplexers, and multiplexers. So here's our equivalent circuit for a 12th order Combline filter. The resonators are across the bottom here. The first resonator is tapped, so these two transmission lines represent the first resonator, and here's the tap line. These transmission lines represent the tuning screws for the resonators. In this case, we're using resonator loading, where the screw can penetrate a hole in the top of the resonator. This transmission line is actually a correction factor for the tapping. This is from a paper by Bud Crystal. The impedance of this line depends on the impedance of the first two resonators and also the first two couplings. And you can see the equations for that computation here. And the result is actually a relatively high impedance transmission line that happens to be negative. But again, this is a correction factor rather than a real transmission line in the final filter. So here's our first channel. The second channel, of course, looks very similar. Each one of these requires 24 variables to optimize. And again, here's our top level MUX schematic. And right now, the two channel filters are actually doubly terminated. We're starting with doubly terminated designs here. There's actually no need to synthesize a singly terminated design because the optimization process is so robust, it can capture the passband here for both channels. And basically, we're going to turn the two channels into singly terminated filters through optimization rather than synthesis. So this is the starting point for our optimization. Again, the optimizer is looking at the reflection zero frequencies here in both channels, and of course they're independent of each other. So now we can start the optimizer, and again the optimizer can look at a single schematic, or in this case, since we have three schematics for the channels and for the top level, we tell it to look at all the schematics when it's looking for variables and reflection zero frequencies. And then we need to tell it that the schematic called MUX is the top level schematic. So if we hit the optimize button, the optimizer will bring both channels to a nearly perfect equal ripple response. And we're working again on 48 variables here simultaneously. But the analysis engine in Microwave Office is quite fast. And in fact, in about 7 iterations of the optimizer, we've got a very nice looking diplexer here. Now, notice we started with the two channels pretty close together. In fact, this spacing is 1/8 of this bandwidth of an individual channel. So even with this starting point where the channels are very close together, we can bring the optimization in using the optimizer. So now to make this diplexer contiguous, we simply walk the two channels closer and closer together by moving the band edge frequencies in small steps. And this next schematic or next project shows you the final step in that process. So we've been walking the two channels closer and closer together, and now we're ready for the final optimization. So we can start the optimizer again again, we need to tell it all schematics, and the top level schematic is called mux, and we hit the optimize button. And we've got a very good solution. If we look closely in the crossover region, it's not quite perfect, so we can run the optimizer one more time. And now it's even more perfect. And notice it's equal ripple return loss right through the crossover region. And this is only possible by adjusting the band edge frequencies here very, very carefully. There's actually a spurious solution here where this will look correct, but there's some problems in the transmission of both filters up here. And that spurious solution we find both when we're optimizing here and also when we're tuning in the lab. So it's obviously possible to design contiguous diplexers and multiplexers, and there's really no limitation as far as EQR opt is concerned. We can have any number of channels, any number of variables, and because the process is so robust and stable, I think just about any design is possible.